So I have here yeah, okay. So my talk today is indeed about high power multipliers technology at ACST, and outlook is as following. I will first present, make a short introduction to teragas technology. Well, I know everybody is an expert in teragas technology, but this is my view. Everybody may have a different opinion and views. So I will present my short introduction, and then I will pass to introduction to ACST in Germany, and then we will discuss. I will present the recent achievements of ACST in field of generation and detection of teragas signals. So, yeah, electromagnetic spectrum is very wide, and we see in the center teragas region. You know that properties of teragas waves have some particular properties which are unique in the spectrum. For instance, they can penetrate through many materials similar to X-rays, but the difference is that the teragas radiation is not ionizing, so it is light compatible. So it's not it's compatible with human body. And on other way, it is similar to microwaves. It means microwaves also penetrate through many materials, but teragas frequencies, due to shorter wavelengths, has a better resolution for imaging applications. So that's one property. Another property is fingerprint of many materials. So you know, most of material have some resonances, which often fell in the teragas range. And if you can investigate these resonances, you can definitely say or conclude what kind of material, what is temperature, what is pressure. And this feature is very convenient, very useful for such science like radio astronomy. You know, for instance, you do not need to fly to Mars to see whether there is water vapor in atmosphere, in Mars atmosphere. You can just look to the reflected light from Mars from here using a telescope, millimeter wave or submillimeter wave telescope. So, of course, there are some other issues, but this is another topic. Another potential for teragas technology, of course, is data transmission. High-speed data transmission. So I think this is clear for everybody. So the fields of applications are, of course, in space. The space was the driven force for the development of teragas technology in the world because of radio astronomy, as I just told. Then, of course, this technology transfers to terrestrial applications, and it found first industrial application is scientific research, so scientific instrumentation for research and development laboratories. And I think at the moment this is the biggest real industrial application for instance, frequency extenders for network analyzers or spectrum analyzers. So further industrial applications are, of course, security. It is like body scan. And related to this is also imaging concerning the industrial quality control. Um, well, and of course, then data transmission systems applications. So of course, okay. So you know that the terahertz frequency is so terahertz range is so called terahertz gap because this frequency range are too high for traditional microwave electronic devices to operate. So the microwave electronics have some particular cutoff frequency, which is usually limited their operation in terahertz regime. And at the same time, if its frequency of terahertz frequency is too low for photonic electronics because of some limitations of quantum energy states at room temperature, basically. Okay, yeah, in 1980s, 18th and the 90s, there was an increasing interest in terahertz technology for space application, as I just told, ESA and NASA and other space agencies. And in Europe, several companies were working on the module level to do terahertz receivers, which basically need mixers, multipliers, and detectors. But there was no European supplier of Schottky components for that. You know, the only supplier of Schottky components, so Schottky diodes, there was VDI in the USA, and only supplier worldwide. You know, and in the 90s and 2000s years, VDI started to develop own terahertz modules and systems, and therefore they came in direct competition with European companies, and ESA, European Space Agency, had particular doubts of availability in the future availability of short components for European needs, and therefore pushes the development of European Schottky technology. And one of the portions and research of the scientific research entities was the Technical University of Darmstadt, where I came to. Darmstadt is in Germany, of course, not a group of Professor Hartnagel, and where I joined in 2000, and but later is one of the most successful groups in the Europe in the development of this Schottky technology. Then ESA understood that the German universities are not the best entities to invest money, because people come to do the PhD and then work, develop technology 5-6 years, and then go away to the industry, leave the university, and new people come, and they have to start everything from very beginning, or at least to start to learn this. And ESA and European companies needs continuously supplier of such of this technology. That was the questions. The request appears to make a company who can continuously supply this technology. And I, with my colleague Cezare Sidlo, was at Cezare Sidlo was not working with this technology, but we together founded this company in 2006, ACST, and this ACST becomes the first European supplier of Schottky components for terahertz applications, and the second company worldwide. So, hence, next year we are we have a jubilee of 15 years alive. You can congratulate my colleagues with that. This is our group. We make a trip. It's a little bit old. It's 2 years ago. Now the group is a little bit. The team is a little bit larger. It's a little bit different. We changed it. Now we are about 20 to 22 people, something like that. You know, my dog in the center here. Okay, so if you're looking at on this history, so in 2006 we found the company. In 2007, my colleague Cesar Sidlo and me built the first quasi-optical terahertz detector, which works from 50 gigahertz to about 2 terahertz. And this was the first demonstration worldwide, indeed. Unfortunately, at that time, we could not establish the fabrication, the industrial, let's say, reproducible process for fabrication of this. And VDI was the first putting this such similar detector on the market. But okay, this is the story, funny story we can discuss when COVID is away and we can stay somewhere in the cup of beer to discuss about. Okay, in 2008 we got the first ESA development project. So then followed by several milestones with the appearing of new technologies. Like this was in 2010 we developed the first team DAOs process, including terahertz and MMSs, and one of this picture shows, for instance, a 1.1 terahertz RTD based oscillators, which is done in collaboration with my colleague Michael Feigenhoff. At that time, we were in the same office at the TU Darmstadt. Okay, but later the team started to grow, and TU Darmstadt. So just to note, up to 2013, we were working in the laboratory of TU Darmstadt, technical research Darmstadt, and then, but since we started to grow the team, it was too much for. We need a separate facility, and in 2013 we moved to separate facility in Hanau. You see here we built here's a big air conditioned system, which is suitable for maintaining 300 square meter clean room facility. Then in 2014, we entered the big ESA mission, which is called METOP second generation, with a range of diodes. We were the main supplier of Schottky diodes, I think. And the whole mission, I don't know, METOP second generation, you know, it is Earth observation of ESA, and one of the biggest ESA missions, and I think it's the first commercial one. It is in framework of this mission is people are going to start a set of satellites, a series of satellites to cruise around the Earth to get data from the Earth, from climate changing and so on, like temperature, water temperature map in the ocean, or how the you know the air masses moves in the atmosphere and so on. And this directly related to our climate on the Earth and weather forecast and so on. So therefore, it's very important for every nation. Doesn't matter either it is developed, it's rich or poor. Anybody is living on this Earth and on this planet, and this is important for everybody. So we SST is one of the most base supplier of Schottky diodes among of 8 of different Schottky diodes involved in this mission. 6 of them are provided by SST. So this mission has instruments up to 664 gigahertz, so different channels, frequency channels, and yeah, okay. And also we SST is delivering a detector for 89 gigahertz direct detection radiometer. So we, as I just told you, we are fully involved in this mission. So in 2016 we established our not established, but we demonstrated first first results of our high power multiplier technology, what in fact is the topic of my talk today. And in 2020, we just recently, a few weeks ago, delivered to our customer the first DNA frequency extender from 140 to 220 gigahertz. It's really, it was a great project. Our distributors got this project from the customer. I don't know how. It was quite cheap. I think we invested maybe 3 to 4 times more money in this development project than we got from the customer, but it was our first step on a system level. And it is very nice, and I will show later the performance of this. Okay, the ACST is a relatively small team, as I told, about 20 to 22 people, but it's highly qualified, and the ACST is very research and development oriented company. So you see here the list of research and development projects in within last 10 years. The green are ongoing, the blue are finished, successfully finished. You see most of the companies, most of the projects are financed by ESA, by European Space Agency, but we have also European Commission project like IFOS and FP7, or we have also Teraapps and Horizon 2020, and currently we are also in teraoptics involved, also on Horizon 2020s, and yeah, some ongoing projects are coming. Currently, you see here two long projects. As I told, it is ESA method duration procurement of detectors and diodes. They had to be finished probably 1 or 2 years ago already, but you know, it is always delaying. Is the same with this project, like Teraapps and NET. They had to be finished, but due to Corona issue, they are delayed, and other projects which are ongoing currently. So just shortly, so the ACST is placed quite close to Frankfurt Airport, about 40 kilometers, 30 to 40 kilometers. So it's easy to reach. Welcome when COVID is away. Welcome to visit ACST. So we have our clean room facility. Here's yellow room for photolithography process. This is assembly room for assembly and DC test. So for instance, here is wire bonding. We have also facility for reliability testing because yes, you know, ESA project reliability plays the central role on the most important, and that's why we decided to establish our reliability test facility in house. Products, yeah, core competency. So Yeah, we are experts in design and fabrication of discrete Schottky diodes and teragas MICs. We have quasi-optical teragas detectors. I think now, I think we are only in Europe, and for these quasi-optical teragas detectors, up to 2.5 teragas, and our competitors is the only VDI in USA, at least according to my knowledge. Mixer multipliers detectors, yes, we developed this everything in-house, up to systems, and offer also series for environmental qualification tests. SST has also original technology, developed technology. It's called film diode process. I think SST is the only. So this technology has been developed by ACST, and is particularly developed for high frequency applications, for sub-millimeter waves and teragas applications. And with this technology, I think we have some advantages in view of performance against other competitors worldwide. It's a little bit more complicated, but as I told, we have advantages in performance, and these give us opportunity to get state-of-the-art performance multipliers and mixers. And that's exactly what it is written here: integrated diamond key spreader and for high power multipliers. So that's one of our core business nowadays, and we are proud to be really the worldwide leaders concerning performance of multipliers in terms of power and bandwidth. There are also other companies who can provide either high power or bandwidth. With our technology, we can provide both, and that's our strong position. And of course, as I just told, SST has a considerable space heritage, not only with ESA, but also with other space agencies, including Asia, and even we have some collaboration with NASA. Strong position of the SST is that we have the whole development chain in our hands, in our in-house, starting with discrete components, I mean Schottky diodes and MMICs, which we use for development and fabrication of modules like mixer, multipliers, detectors, and so on. And we use also these multipliers and mixers to build systems. And that's our strong position, because most of the companies have only multipliers, I mean modules, or system level. So, and then depend, of course, of they can only do at the system level. They can only provide what's available on the market concerning the modules, and the modules can only provide what's available on the market concerning the components, Schottky components, and that strongly limits the performance. Our advantage is that we can, if we target a particular performance of the system, then we can start from development of particular suited components, and that's a real great advantage. I think only few, maybe such companies worldwide have this opportunity, and ACS is one of them. Yeah, this slide shows again just some story of these projects of method second generation with ESA. It started in 2009. First project. It was a series of development projects. We started in 2009. We were working with Airbus at that time. Well, at that time, Airbus was called EADS. It was later renamed in Airbus for development of this kind of 89 gigahertz detectors and diodes and detectors. It was particularly developed. And then we have a reliability study, which is finished in 2017, preliminary reliability study, just to, is I wanted to see whether this is feasible for network second generation. And then, of course, now ongoing is flight hardware, where we develop and fabricate and qualify detectors for height, which have to be installed on satellites and used in space. I think even now these weeks we have to deliver, I don't know, maybe 12 for such detectors. And currently people are intensively working in the lab to build up this and to qualify. Measurements, qualification it's a lot of work. Okay, so this picture shows that just a whole instrument. It's a 89 gigahertz direct detection radiometer, which is built by our project partner in Finland. It's called DA Design. And you see in the middle of this instrument stays placed our detector, which is like a heart of this system. And of course, this project now is led by Airbus, France, UK, Germany, and so it's a big project with big players inside. Yeah, I just told about this. I think there's nothing much to tell about. He shows that just a customer product. It's also a transceiver, a 300 gigahertz a frequency extender for 300 gigahertz frequency extender for FMCW radar. I think maybe I have another slide later to discuss about to show you, but this is really state-of-the-art radar with which provide about 40 milliwatts of output power and bandwidth of about 50 or 40 gigahertz, which is nobody can provide this at the moment. I think. Well, there is JPL which can do such systems on broadband sources, but no, JPL is not a commercial company. It is a scientific laboratory of NASA, and they do everything in integrated monolithically integrated structure. And such a system, if for instance from ACST cost about maybe 50,000 euros, from GPL would definitely cost 10 times more. So it's not payable by industry. Okay, let's go away. ACST is working, of course, worldwide. We have customers everywhere, in Asia, like China, Japan, Australia even, and North America, Europe, everything, just for information. So I think it's enough to work about to talk about ACST. Let's go to high power electronics, millimeter wave or sub-millimeter wave power electronics. Why we need high power at millimeter waves? The possible application area are millimeter wave radars, for instance, or interior chips for local oscillator sources and terahertz heterodyne receivers. You know that people want to go to 1 terahertz to 2 terahertz. There are also attempts to go up to 2.5 or 3 terahertz receivers with Schottky technology, but they need a local oscillator sources, and this is not simple. So typical local oscillator source for typical directional diodes needs a couple of milliwatts of power, and it is definitely not easy to get it at 1 terahertz, for instance. And yeah, I'm sorry, yeah. Then sources for wireless millimeter wave data transmission systems. Yes, of course. Here you need also high power in order to achieve to increase the distance of communication without, of course, there is an approach to increase the antenna gain to 25 to 30 to, I don't know, 35 dBi, and you can, with the increasing antenna gain, you can increase the distance of communications. But you can imagine if you have a very high antenna gain, so slightly vibration, you lose the link. And that's why the high antenna gain is not really good for a stable communication. The only alternative is to increase the power. So that's, you need power. Illumination sources for security active imaging. I have to comment here not for only security active imaging, but also for industrial quality control. The most okay, of course there are detectors which are very sensitive, which can detect natural target radiation from body or from target. But these detectors are usually not very suitable for using in big arrays, or are very expensive, or they have to be cryogenically cooled and not very practical for practical applications. Therefore, usually less sensitive detectors are used for imaging, like microbolometers, room temperature microbolometers, and there are also some companies worldwide which use and produce such terahertz cameras with arrays of thousands of pixels. But these detectors are not very sensitive, so they cannot detect the natural radiation of terahertz radiation from body. Therefore, they need illumination sources to illuminate the target. It is, and that's exactly what we need. One of the application for millimeter of sub-millimeter wave sources. And of course, there are new emerging applications which come. A lot of people work on terahertz technology at the moment, and new applications appears, and yeah, the only problem is that lack of power, lack of sensitivity, and very high costs, prices. Okay, what we have at the moment offer, what our technology offer at the moment concerning the high power millimeter wave sources. So there are vacuum electronics like BDO or klystron. They indeed can watts or even kilowatts of power, but these are bulky. So klystron, for instance, can provide really kilowatts of millimeter wave, but they are very bulky. They use high power, high voltage. They need several thousand volts cathode voltage to accelerate this beam and so on. And they are very usually, well, they're noisy. It's not very, the signal is not very clean. They may be not very stable, and lifetime is also limited because, yeah, and of course, complexity. Another alternative is solid state oscillators like GaN diodes or impact diodes, or there are a few other possibilities. Well, again, we are talking about power electronics, not about photonic sources. Photonic sources are very bandwidth, very clean signals, but they are very low power. We are talking about milliwatts and tens and hundreds of milliwatts. Okay, GaNs and impact, but they have also some drawbacks in technology. They are not very reproducible. They are quite very limited in bandwidth, because these usually are resonant diodes, resonant devices, and they are also limited in frequency. I know GaN and impact diodes which provide considerable power, yeah, in the range of 100 gigahertz or something like that, but not much more above. Above that, okay. Another option is the power amplifiers. Okay, if you can oscillate, extract small oscillations, small power by oscillator, and let's say at millimeter waves, and can amplify by amplifiers, then it's okay. But the state-of-the-art amplifiers are gallium nitride based, and they are also limited to frequency below 100 gigahertz, roughly. There are some new developments, recent developments, which go to 200 gigahertz, but this is newest development and is not really available for industry and for scientific community in the world, because it is strongly restricted by USA export restrictions. So the only, and also there are Schottky-based multiplier chains, but they are limited in power handling capability at the moment using standard diodes. So in fact, the Schottky-based multiplier chains is the most the best, commonly chosen approach. The oscillations are generated below 100 gigahertz by either GAN or IMPAT or anything else, or even BWO, and then amplified by available power amplifier. So there are gallium nitride MMICs, high power amplifier, which can amplify signals up to maybe 2 watts. Current state of the art, I think, or maybe even 4, but more commonly used 1 or 2 watts output power. And then people use Schottky-based multiplier chains to upconvert this power to higher frequency, to the second or to the third harmonic. And here, as I told, this is commonly used approach: power amplifier up to W band, and then power combined multipliers above W band, because the current Schottky-based multipliers are limited in the power handling capability. And this slide shows an approach of power combining approach. So that, I didn't tell that. It's, since Schottky biased multiplier chains cannot handle enough power, usually this input power from gallium nitride MMIC of 1 watt or 2 watts is divided in several channels, and these channels are upconverted separately, and then power is combined again to get high power. And this brings to such systems. You see, this it's a very complex system. I think this is it's a result of work or collaboration of radiometer physics from Germany with ACST, so RPG and ACST, and is published in 2015. We got a great power of about 100 milliwatt. I'm sorry, about 100 milliwatt at 200 gigahertz, and this was really the great results, state of the art. But you see how complex it may be. So you have power. Power splitter, and then parallel chains, then power combining, and so on. And here is even a more complex example. It's just an abstract example to if you need 50 milliwatts at 300 gigahertz, and you have 1 watt at 75 gigahertz, which is commonly is commercially available amplifiers for this. Then you cannot handle this power with a single multiplier, so you have to make a power divider in 4 channels, use 4 parallel multipliers, doublers for instance, then combine these doublers separately, and then use again 2 channels for upconverting from 150 to 300 gigahertz, and then power combining again. And that's such a you can convert this power from 75 gigahertz to 300 gigahertz, you lose 13 dBm, but you get this 50 milliwatt at 300 gigahertz. The SCST approach is to develop, one of the goals of the SCST was to develop high power multipliers which can handle this power of 13 dBm, so 1 watt, in a single multiplier, in a single doubler. And we have achieved this. And in this case, we can replace the whole such a system just by a system like this. And this, you can consider it is a bandwidth of 17%. It is a great result. So in this case, we using our, I will tell later, we have a power handling capability of several times more than traditional multipliers, and we have a very high or relatively high bandwidth. Just to tell, this is high efficiency doubler, and for this high efficiency doubler, the best supplier worldwide, which VDI has about 10% of bandwidth. We have 17%. Just for comparison. So in this case, we get the bandwidth, we get the strongly reduce the system complexity, we increase the reliability because the simpler the system is, the most reliable it is, and of course volume, weight, and costs. And also I have to mention efficiency, because in all these power combiner, power dividers and power combiner, there are losses always. And in this case, we get rid of these losses. So that means that's our great result. How can this be achieved? If you look on, I don't know how much time I have, maybe.
It's 15 minutes left of your session.
Okay, I have to accelerate then. Okay, I think this I told already at the introduction of ACST. We have all the development chain in our in-house. Therefore, we have a short development loop for which is very important for very fast development iterations. The limiting factor for conversion efficiency. There are some limiting factors in design and fabrication, electrical characteristics of the diodes, and so on. And if you look on this slide, we have these ACST solutions for these challenges. For instance, diodes, ACST Varactor diodes, which are used for high efficiency multipliers, have near to theoretical limit of breakdown, which is essential for high power applications. And in comparison with diamond heat split, which I show in the next slide, it gives beautiful results. Yeah, like here, you see thermal limitations. It's also so there are limiting in conversion efficiency and limiting power handling capability. And power handling capability, there is limiting electrical limitation and thermal limitations. Electrical limitations is solved by good RF design and ACST Varactor technology, and thermal limitations is solved by at ACST by monolithic integration of diamond heat spreader. So this slide just shows shortly what I mean with diamond heat spreader. So this is Varactor. You see here the nearly ideal IV characteristics of ACST Varactor technology, which shows breakdown of 15 volts. And the theoretical limit for this doping concentration is 15 volts. So we really close, we are really reach the theoretical limit of gallium arsenide material in breakdown voltage. And this part on the right part of the slide shows an example of integration of Varactor array on diamond heat spread substrate. This allows us to increase the power handling of these diodes by a factor of, I say, maybe, yeah, between 5 and 10 times, 10 times. Uh, Theoretically, is at least 10 times. Practically, we got 5 times better power handling capability. But to be honest, we could not kill our diodes at the moment with available power. So it's not investigated until the end how much better power handling capability our multipliers are, but at least factor, yeah, 4 to 6 better than traditional multipliers. Okay, this slide shows that again how it looks like. So these diamond substrate diodes are built on substrate, also on different type of substrates, and then these are built in the split block technology, and then these split block are close together, and we got such modules like here as on right hand of the slide. And this slide just show shortly inside how it looks like inside. I think these particular views are published several years ago, and these are again, for instance, this is a 600 gigahertz tripler, which provided more than 5 milliwatts from a single device. This is absolutely state of the art, at least at that time. It was about 5 years ago. And yeah, this use SST film diode technology with integrated diamond heat spreader here and an array of Schottky Varato diodes. Yeah, of course, this it takes a lot of time, and it's not very easy to make a successful design, which in terms of power handling capability and conversion efficiency. But we managed to do this, and our models are scalable to higher frequency. For instance, you see here we have one which provides about 150 gigahertz, 135 to 160. About it is written here 180 gigahertz, but we got more than 200, and we could not kill this diode, this multiplier up to now. We specify up to 150, up to 180, because we are not sure of higher power. This has to be tested, and this could be just scaled to higher frequency band, up to about 165 gigahertz or 170 gigahertz. Okay, and the same for higher frequency band, for instance, about 300 gigahertz to 350 gigahertz. So it's scalable fully, and we get very good efficiency. So I think the efficiency is not written here, but we have really standard data of efficiency. For 150 gigahertz, doubles about 35 to 40%, and for 300 gigahertz, about 25 to 30%, which is really state of the art. This slide shows how these multiplier chains are working together. If you can back, for instance, these two multipliers are particularly designed to be used with each other. So that means if you have an input power of about 1 watt at the input, so we use this multiplier plus this multiplier, and we got times 4 at 300 gigahertz, 40 milliwatts or 50 milliwatts at 300 gigahertz. And this just shows that how this setup is done, how it works. In this case, we use an attenuator here, just in order to not overdrive the multiplier. But as I told, even with available power in W band, we could not kill the diodes, and this has to be investigated in order to be sure that we can specify these values. Nevertheless, we provide up to 50 milliwatts with in such a wide band, 270 to 320 gigahertz. which is really state-of-the-art worldwide, and as I told before. And I have to mention that this is not that just like in university work usually just make somehow, demonstrate it, publish, and forget. No, this is a really commercial product. Here, for instance, you see the comparison of 4 sources about 300 GHz, and you see rather similar results, similar output power from all of them. On the right side, pictures on the top is written, it's shown 300 GHz transceiver, and the bottom is 300 GHz source. Okay, also it's possible to, so for 300 GHz is have a block diagram very similar to that, but instead of this tripler is a doubler. Now we thought, okay, if we this doubler by a tripler, then we get a 500 GHz source, and we have done this, and we got about 20 milliwatt at about 500 GHz with the bandwidth about 15%, which again is very impressive power. When I tell my colleagues project that we can project colleagues or potential customers that we can provide 20 milliwatts at about 500 GHz with just a bandwidth, they just do not believe. So another aspect is price. Yeah, if you do such a system like this, a price of a 500 GHz or 300 GHz source is about 35 to 40,000 euros. It is too much expensive for practical industrial application. It is suitable for development, for research and development, and for some tests, but for real industrial applications, it is too much. So you can imagine if only the source costs 40,000 euros, then the detector should cost again, I don't know, 40,000, then the management, the rest of system, and it costs about 250, 200,000 euros. There are no much chance to go to get on real industrial applications. But we make an research and calculations, and if we integrate all these components in a single module, which is in fact possible, then we can reduce the price down to about 10,000 euros. And another option, if we increase the series of production, for instance, hundreds pieces of 1,000 pieces per year, then we can get another strong reduction of the price, which goes down to about 5 kilo euros per pieces. And this is already the price which becomes attractive for industry. And that is the way to go. So first to develop, to demonstrate performance, then to get money to make development for full integration, and then to find an application and customer who may implement really industrial application, and then we can really go to this price. And that point, it's not far away. I believe this point can be achieved within few years. Okay, these slides just show again more details of a 300 GHz frequency extender of FMCW radar. With state-of-the-art results you can read here below. And yeah, this is a list of other sources available at the LCST or in progress in development at the moment. You see up to 525 GHz. SST is also working on full band multipliers, which is very interesting for measurement instruments. And finally, as I told at the very beginning, we are very proud to present our first DNA frequency extenders up to 140 to 220 GHz with state-of-the-art performance. You see here the output power. It's about several milliwatts and the whole band, which is really state of the art, and the dynamic range is well, the specified dynamic range is -105 dB. We reached a typical about 110 dB, and as I told, I'm very proud with these results, and proud to show you. So we have nice housing with a nice logo SST there, and yeah, that's our next step to go to. Okay, that is the end of my presentation. Thank you very much for your attention, and you are welcome for any question. So the talk is open to discussion.